Find slope equation and deflection equation for cantilever carrying point load at its free end as well as at a distance d from the fixed end by using double integration method. We will find out slope equation and deflection equation for cantilever beam when concentrated load applied at the free end by using double integration method. If we observe the diagram, then beam AB where the end A is fixed and at the other end B concentrated load or point load W is applied. The total length of the beam is mentioned L. So how to find out slope equation? For that we will consider any section on beam AB. So I will consider here the section XX and it is at a distance x from this end A. So what is the remaining distance? So remaining distance is equal to L minus x. Now we will find out the slope equation. So we have to first find out the bending moment at this section XX. For that we will first consider the sign convention. When the moment is in the clockwise direction, we will consider negative sign, and when the moment is in anti-clockwise direction, we will consider positive sign. Now how to take the bending moment of this concentrated load W along this section XX. So we know that load multiplied by distance in between this load and this section. So if I move the compass about this section X in the direction of W, then there is clockwise direction. So we will use negative sign. So bending moment is minus W multiplied by the distance L minus X. So we will take here the distance minus W inside the bracket L minus X. So this is the equation number 1. Now bending moment at any section. So we have formula bending moment at any section mx is equal to EI d square y by dx square. Now if we compare equation number 1 and 2, then these two are same. So we will take the right hand side. So EI d square y by dx square is equal to minus W inside the bracket L minus x. So this is the equation number 3. Now to find out slope equation, we will take the integration on both sides. So this is the first integration. So how to take this integration? So we know that EI dy by dx is equal to, now here minus W constant term we will consider as it is. Now what about this L? So integration of inside the bracket L minus x. So I will take here Lx minus, now what about the integration of x? So integration of x raised to n is equal to x raised to n plus 1 divided by n plus 1. So here x raised to 1, so it is equal to x square by 2. So I will take minus sign as it is, x square by 2 plus c1, where c1 is the constant of integration. Now how to find out the constant of integration? For that we have to consider the boundary conditions. Now if we observe in this equation number 4, here dy by dx is known as slope. Now if we observe when the point load applied at the end B, then this end A is fixed end. So there is slope is equal to 0. That means this value dy by dx is equal to 0. And what is the value of x at this end A? So at end A, x is equal to 0. So we can say that at point A, x is equal to 0 and dy by dx is equal to 0, and these are the boundary conditions. Now when we apply the boundary conditions, then on left hand side 0, on right hand side 0. So C1 is equal to 0. Now when we put this value of C1 in equation number 4, then we will get the slope equation. So slope equation is equal to EI dy by dx is equal to minus W inside the bracket L minus x minus W inside the bracket Lx minus x square by 2, and this is the slope equation, and it is equation number 5. we will find out slope at B. If we observe the diagram, then at B value of x is equal to capital L. So this is the slope equation, and instead of small x we will put the capital L. So what will be the equation? So EI, now dy by dx is nothing but slope. So dy by dx at B is equal to minus W L square minus L square by 2. So here we will make the common denominator, that is 2L square minus L square by 2. So when we simplify this, then we will get now dy by dx at B. So we will measure the slope in terms of angle theta. Now we will understand with the help of diagram. So suppose because of this point load or concentrated load W, the deflection of the beam is in the downward direction. So I will show here the deflection. So here is the deflection. So the angle with this horizontal line is known as this theta B. Now why B? Because this is the deflection at this free end. So this angle is known as theta B. Now this theta B is equal to minus W by EI into L square by 2. So this is the equation we will find out slope at B. So I will make the square. Now we will find out the deflection equation. So again we will take the integration of the slope equation, that is the equation number 5. So EIY is equal to minus WL. Now instead of x, by using this formula we will write x square by 2 minus. Now what about x square? It is x cube by 3, but in denominator 2 is there, so 3 multiplied by 2 is 6 plus C2, where C2 is the constant of integration. So this is the second integration, so we will use here the letter C2. Now how to find out this C2? So we will apply boundary conditions. If we observe, this is the equation number 6, this y is nothing but the deflection. Now if we observe at end A, it is the fixed end. So suppose there is the deflection of this beam AB, then at end A deflection is 0 and the value of x is also equal to 0 because it is the fixed end. So we will put the boundary conditions. At end A, x is equal to 0 and y is also equal to 0. So these boundary conditions when we put in this equation, then we will C2 is equal to 0. So when we put C2 is equal to 0, then we will get deflection equation. For deflection equation is EIY is equal to minus W Lx square by 2 minus x cube by 6. So this is the equation number 7. We will find out deflection at end B. So if we observe at end B, value of x is equal to capital L. So instead of x, when we put capital L, then we will get YB is equal to minus W by EI, because this EI term we will transfer to the right hand side, in the bracket L cube by 2 minus L cube by 6. So when we simplify this, then we will get YB is equal to minus W by EI L cube by 3. So this is the deflection at the end B. So we will make the bracket. Now we will show this YB in the diagram. So here is the deflection. So this is the original position of the end B and here is the final position. So this vertical distance is known as YB, that is the deflection at the end B. Now if we observe, here is the negative sign because this deflection is in the downward direction. Find out slope equation and deflection equation for cantilever beam carrying point load at a distance d from the fixed end. If we observe the diagram, there is beam AB of total length L and the point load W is acting at point C and it is having distance small d from the fixed end A. And we have to find out the slope equation as well as deflection equation by using double integration method. Now we will first find out the bending moment along the section XX. So we will consider any section XX in between the fixed end and the point load W. So I will consider this section XX and this section XX is having distance small x from this fixed end A. Now if we observe the diagram from this point load W, what is the distance from the section XX? So this total distance is small d, so d minus x. Now we will find out bending moment about the section XX. So we know that bending moment is equal to load multiplied by the distance. So if the direction of this moment is in clockwise direction, use negative sign, and for anti-clockwise direction use positive sign. So if I move the compass about the section XX in the direction of W, that is in the downward direction, then there is clockwise direction. So we will take bending moment minus W multiplied by d minus x. So this is the equation number 1. Now we have formula for bending moment along any section, and it is EI d square y by dx square. So this is the equation number 2. So if we observe equation number 1 and 2 are equal, so we will equate the right hand side. So we will write EI d square y by dx square is equal to minus W d minus x. This is the equation number 3. Now we are going to use double integration method. So to find out slope equation, we will take the integration, that is the first integration on both sides. So EI dy by dx is equal to minus W, here dx minus x square by 2 plus c1, where c1 is the constant of integration. So to find out the slope equation, or to find out the value of c1, we will apply the boundary conditions. If we observe this equation, then dy by dx is nothing but slope. Now at the fixed end A, value of x is equal to 0, and because of point load, if this beam is getting deflected, then at this point A, deflection or slope is equal to 0. So at this point A, we can say that x is equal to 0, slope is equal to 0, and deflection is also equal to 0. So the slope is nothing but this dy by dx. So x is equal to 0 and dy by dx is equal to 0. So when we put this value in this equation number 4, then we will get c1 is equal to 0. So final equation is, that is the slope equation, EI dy by dx is equal to minus W dx minus x square by 2. So this is the equation number 5, and it is known as the slope equation. So we can use this equation to find out slope at any point. Now we will use this equation to find out slope at point C. Now if we observe the point C is having distance d, that means we can say that x is equal to small d. So how to find out? So instead of this x, we can put d. So this dy by dx is nothing but the slope. So slope, how we will measure? In terms of theta. Now if I show here, because of this point load, this beam is getting deflected. So I will show here the deflection. So this is the deflection. Now at point C, how to measure the slope? So here is the original position and here is the final position. So slope is measured in terms of angle theta, that is theta c. So instead of dy by dx, we will write theta c. So EI I will transfer to the right hand side. So minus W by EI d square minus d square by 2. So when we simplify, we will get theta c is equal to minus W d square by 2 EI. We will find out deflection equation by taking integration on both sides of the slope equation. So the equation will become EIy is equal to minus W inside the bracket dx square by 2 minus x square by 2 is having x cube by 6 plus c2, where c2 is the constant of integration. So how to find out the value of c2? Now if we observe in this equation, y is nothing but the deflection, and at end A, when x is equal to 0, then deflection is also equal to 0. So we will apply these boundary conditions. At fixed end A, x is equal to 0 and y is also equal to 0. So these are the boundary conditions. So when we apply, we will get c2 is equal to 0. So we will get the deflection equation EIY is equal to minus W dx square by 2 minus x cube by 6. So this is the equation we will use to find out the deflection. Now we will find out deflection at C. If we observe the diagram, because of this point load W, here this beam is getting deflected, and I will show here the final position of C. So here is the final position of C is known as C dash. Now at the same time this B is also having the final position, and it is B dash. So here is the B dash. Now how to find out the deflection at C? So we know that at point C the value of x is equal to small. So equation will become, instead of as a yc, because the deflection at point C, EIYC is equal to minus W. Instead of x we will put d, that is d cube by 2 minus d cube by 6, and therefore yc is equal to minus W d cube by 3 EI. So we will simplify this bracket. So I will make the bracket. This is the formula to calculate deflection at point C, where C is the point of application of the load. Now how to find out deflection at the end B? Now if we observe, I will make one construction. I will extend this point C dash, and I will drop one perpendicular line on the B dash. And here is the point of intersection, that is point D. Now what is this total deflection at B? That is known as YB. So this YB is equal to BD and plus DB dash. BD plus DB dash. So here will be D. If we observe the diagram, then BD is equal to CC dash and is equal to YC. So YC, that is the deflection at point C, we will put this value minus W d cube by 3 EI. Now what about B dash D? So here is B dash D. So in this triangle B dash C dash D, here is the angle theta C, because these two are parallel line and this is the common inclined line, and therefore we can say that B dash D is equal to DC dash tan of theta C, but this theta C is very small, so tan of theta C is equal to theta C, and this DC dash is equal to BC, and this BC is equal to L minus D. So how we can define this B dash D? So B dash D is equal to L minus D inside the bracket. So value of theta C, that is the slope at point C. So we have calculated minus WD square by 2 EI. Now if we observe, we have to put to calculate deflection at point B, that is the deflection at free end, BD is equal to minus WD cube by 3 EI plus B dash D, that is minus WD square by 2 EI inside the bracket L minus D. Now this negative sign indicates the direction of the deflection, that is it is in the downward direction. So we will take minus sign as a common term. So here is minus inside the bracket plus WD cube by 3 EI plus WD square by 2 EI L minus D. So this is the formula to calculate the deflection at the free end.